Statement. Russia's future sixth-generation fighter as well as its next-generation unmanned aircraft could be equipped with what is described as a radio-photonic radar. If the Russians succeed in developing such systems, Moscow would be in possession of a sensor with far greater range and resolution, high enough to develop a three-dimensional image of an airborne target, than anything currently in operation around the world. Potentially, such a radar system could allow the Russians to develop a weapons quality track on a stealth aircraft if it proves to be successful. According to the state-owned TASS news agency, Russia's RTI group is expected to complete preliminary research and development, as well as build a mock-up of a X-band radio-photonic radar this year. That will determine a principal scheme of building the radio-photonic locator, the RTI group told TASS. That should allow the company in several years to build prototypes of super-light and small-size radars for unmanned aerial vehicles. Photonic radars will be able to provide radio wave imaging when an image has greater details with the possibility to identify the target type, the RTI group told TASS. That mirrors previous statements from the Radio Electronic Technologies Group, which is generally better known by its Russian acronym CRET. The radio-photonic radar will be able to see farther than existing radars, in our estimates. And, as we irradiate an enemy in an unprecedentedly wide range of frequencies, we'll know its position with the highest accuracy, and after processing we'll get an almost photographic image of it. Radio Vision. Vladimir Mikheyev, an advisor to the first Deputy Chief Executive Officer of CRET, told TASS last year. CRET claims to have already developed working prototypes of various subcomponents of their photonic radar. CRET is now working on building a full-scale prototype of the system. Both the emitter and the receiver have been built on the basis of the experimental prototype as part of the R&D work. All this works and performs the location. We emit an ultra-high frequency signal, it is reflected back and we receive and process it and get the radar picture of an object. We see what we need to do to make it optimal, Mikheyev said. Now a full-fledged mock-up of this radio-optical photonic antenna array is being developed as part of the research and development work, which will allow us to test the characteristics of the serial prototype. The Russians are not the first to start developing photonic radars. An Italian-funded project called Photonic-based Full Digital Radar, FOTR, developed the first fully photonics-based coherent radar system in 2014. A photonic radar replaces the traditional electronic circuits of conventional radars with lasers, optical filters and photodiodes to generate very precise, high-quality radio frequency signals. While the photonic radar still uses radio waves to locate objects like conventional systems, the laser allows it to pulse highly tuned frequencies in a broad emission band from the tens of megahertz to possibly up to the hundreds of gigahertz, states a General Electric press statement. Current marine radar and air traffic control typically operate in the 1 to 12 GHz range, with higher frequencies typically meaning more precise detection of objects. Lead photo researcher Paolo Gelfi, an electronics engineer with Italy's National Inter-University Consortium for Telecommunications, CNIT, described some of the team's research to technologist. We are defining the position, speed and even the shape of big cargo ships in and outside the port, Gelfi said. Using a laser instead of traditional radar electronics means we can detect more accurate positions of objects. We can also detect smaller objects farther away because our system produces lower noise in the radar signal. The FOTR team published their findings in the peer-reviewed scientific journal Nature in 2014. The proposed architecture exploits a single-pulse laser for generating tunable radar signals and receiving their echoes, avoiding radio frequency up and down conversion and guaranteeing both the software-defined approach and high resolution, reads the paper abstract from the Italian team. Its performance exceeds state-of-the-art electronics at carrier frequencies above 2 GHz, and the detection of non-cooperating aeroplanes confirms the effectiveness and expected precision of the system. Other researchers, including one from China, have followed up on the FOTR team's work to address some of the limitations of current photonic radar technology. The signal processing in the sampling receiver is still a main limitation of the operation frequency and bandwidth, reads a paper by Chinese scientists Fengjun Zhang, Guangshui Guo and Shilong Pan in Nature. To down-convert the high-frequency RF signals, microwave photonic frequency conversion and time-stretched analog-to-digital conversion techniques have been proposed, but it is still hard for a traditional radar receiver to process the down-converted baseband or intermediate frequency, band signals if a very large operation bandwidth is adopted. The Chinese researchers posed a solution to that problem in their paper. We propose and demonstrate a photonics-based real-time high-range resolution radar incorporating optical generation and processing of broadband LFM signals, the researchers wrote. In the transmitter, a broadband LFM signal is generated by frequency quadrupling of a low-speed electrical signal applying a single integrated electro-optical modulator. In the receiver, the reflected LFM signal is dechirped to a low-frequency signal based on photonic frequency mixing. The implementation of photonic dechirping can directly process high-frequency and large bandwidth signals without any electrical frequency conversion. After photonic dechirping, ADC with a moderate sampling rate can be used in the receiver and real-time signal processing is realizable. In the proposed system, the bandwidth limitations due to electrical signal generation and processing is eliminated. The maximum operation bandwidth is mainly determined by the electro-optical devices, which can be tens or even hundreds of gigahertz. As a result, real-time radar detection with a very high range resolution can be realized. Meanwhile,